Assalamu alaikum dear students, we're back with another video lesson. In the previous video lesson we were talking about sounds, so we're going to continue to talk about sound a little bit more. So we've learned that sound waves are longitudinal and then they transmit their energy through the medium by making the particles of a medium vibrate. We also said that every sound is made by a vibration. So once these vibrations are passing through the air, it produces or forms regions where air particles are close to one another. We call them compressions, Basha, and then also produce other regions where the air particles are far from one another. We call them rarefaction. And then after that, we were talking about the three types of sounds. We said we have infrasounds. Those are sound waves that we don't hear them. Those sounds are with frequencies that are below 20 hertz. And then we said there are audible sound waves. These are the sounds that is heard by average humans, we can say, or average human ear, and their frequencies range between 20 to 20,000 hertz. And we also have ultrasonic waves or sound waves. Those are sound waves, again, that we don't hear them, but their frequencies are above 20,000 hertz. We've learned about the relation between frequency and wavelength. We also said that if a sound has the least frequency or the lowest frequency, then its wavelength will be the largest. If it has the highest frequency, then its wavelength will be the shortest there. But if all of these are in the same medium, the speed of each one of these sounds will always be in the same medium. So don't fall for this. Don't look at the frequency, say whichever has the highest frequency, that would travel faster. No, because this bin in Wazari, right? No matter what the frequencies are, as long as it is the same sound, it is the same medium, even if it is different sound in the same medium, then the speed of sound will be the same, all right, in the same medium. So, Basha, and then we ended up right at this point here. Today we'll talk about the speed of sound. And the first thing that you need to know, the speed of sound depends on the medium here. So those mediums that we have, we're going to talk about the speed of sound in three different mediums here. But first of all, let's just say speed of sound, Basha, speed of sound. And then, of course, the equation for speed of sound, the frequency times the wavelength, which we've already talked about this, right? But now we're going to talk about three different mediums, Basha. So now we have solids, we can say, or speed of sound in solids, and then speed of sound in liquids, and also speed of sound in gases as well. So the first thing that we have, speed of sound in solids, okay? And then we can say liquids, and of course gases too, okay? Now we know that the particles of a solid are very close to one another, yes? This is the lattice structure, you can say. So these are the particles, these are very close to one another. But in liquid, the particles are, and these are, you can see that, these are very well organized, the lattice structure, you can say, and these are the particles here are, we can say, further apart from the solid particles, and these particles are not arranged, or you can say they can slide past one another. But then for gas particles, because these particles are very far from, or these are very far from one another, and they can, of course, move through whatever the volume that there are in here. Okay, so now how is the speed of sound in solid? Do not forget in here, Basha. So speed of sound or sound travel the fastest in solid. Why is that? Because you can see that, all right, the speed of sound depends on how fast the energy of one particle, right, would be given or transferred to the next particle, and then to the next, and then to the next. Because the solid particles are very close to one another, so we can say the speed of sound in solid would be maximum, Basha. And we can say speed of sound in concrete and all that, it is roughly about 5,000 meters per second. This is how fast it can travel in solids, Basha. It is approximately about 5,000 here. What about in liquid? You can see that the particles are a little bit further apart from solid. So they sound this fast, but not as fast as in liquid. So we can say the speed of sound, it is approximately about 1,500 meters per second. That'll be in liquids. Basha, what about in gases? Right, in gases, the particles are the farthest apart from one another. So the speed of sound is going to be the slowest, which is about, we can say, 340 meter per second, Basha. So these are an estimation of the speed of sound in each one of these materials. Based on this, we can see that the speed of sound in solid, Basha, it is the largest, it's the largest, of course. Liquid, it is we can see that also for liquid it is larger than for gases. Gases would be the slowest here. Here, like the way that we're going to write this one, we'll say speed of sound in solid is larger than speed of sound in liquids, Basha, which is larger than speed of sound in gases. Remember, we're talking about different mediums, Basha. So we have a question also says why the speed of sound is the fastest in solids. Well, the reason why, because this sound is transferred by, or the energy of a sound is transferred by making the particles of a medium vibrate, or how fast one particle gives the energy to the next particle or the neighboring particle. And for solid here, you can see that because the particles are very close, so this transfer happens very quickly, so the sound can travel really fast in solids, but it is less in liquid and it is the least in gases because the particles in gas are the farthest or very far from one another. Basha? So this will be the speed of sound in different medium here. Now there is one more thing you need to know, and that is regarding this. What happens if we increase the temperature of these materials, all right? Or will there be any effect of the temperature on the speed of the sound? The answer is yes, Basha. So if we're going, what exactly happens if we're going to increase the temperature here? So we can say increase, all right? Increase of what? Increase of temperature, right? Or you can say the effect of increase of temperature on the speed of sound here. Once again, we have solids, Basha. We have liquids, and we have gases too, Basha. So once again, solid, right, liquid, and gases here. So what exactly happens? We know the speed, Basha. The speed of this one, let's rewrite it. It is about 5,000 meters per second. This one about 1,500 meters per second. And this is about 340 meters per second. 330, 340, doesn't matter. At this point here, these are their speed. So now, what exactly happens if we increase the temperature of each one of these by the same amount? Let's say we'll increase the temperature of each one of these by 25 degrees Celsius, Basha. So this is what happened. We have different mediums. We're going to increase the temperature of each one of these by 25 more degrees Celsius. So whatever the temperature is, we're going to, increase the temperature of each one of these by 25 degrees Celsius. We'll notice that, right? Let's say that the speed of sound might, I'll just give you some random numbers, Basha. The speed of sound, by the way, what exactly does the speed of sound will happen to the speed of sound if you increase the temperature? But if you increase the temperature, the particles get thermal energy. Now they're going to vibrate faster. And the faster the particles can vibrate, we can say the faster they transfer, or it transfers the energy from one particle to another, which overall makes the speed of sound in that medium or in that object faster here. But there's one thing you need to be careful here. Even if you increase the temperature of a solid, Baba, because the solid particles are, very close to one another. So even once you increase the temperature, would that allow the particles to, for example, vibrate back and forth that much? No, because these are really bound close to one another. They don't have enough space to travel that much back and forth, faster and faster. So the speed of sound, it might increase, let's just say, it might increase by only 10 meters per second, Masha. That is how much increase if we increase the temperature by 25. What about in liquid? Because in liquid, the particles are further from one another. So now the particles have more freedom to vibrate. And of course, the more freedom it vibrate, you can say the faster they can vibrate. So the speed of sound that is going to increase more compared to the solid. Let's say the speed of sound in liquid increases by 15 meters per second here. And then what about in gases? Because the gas particles are very far from one another. So once you increase the temperature, now these particles have, a lot of space to vibrate. So they're going to vibrate so much, or there is a lot of space to vibrate in. So in this case, one particle can give their energy real quick to the next or to the other particles here. So the speed of sound, it can increase the most by increasing the temperature. Let's just say 25, meter per second. These are random numbers, by the way. This is how much it will increase in gases. Why? Because the gas particles are very far. So once you heat the gas, these particles gain thermal energy, which converts to kinetic energy or makes the particle vibrate faster. And then the faster the vibration, that means the faster of transferring the energy from one particle to another, which that contributes, make the speed of sound in that for example, in that medium to be way faster. But once again, so now we can say, or you can see the effect on temperature of each one of these states now. You can tell now, once we increase the temperature of each one of these states or medium here by the same amount, you can see that the effect of temperature on gases would be the largest. Basha, why, Gutman? Because the gas particles are very far, so once you increase them, they have the ability to vibrate way more because there is enough free space there, and then that makes them to be way faster here. But once again, even though we can see that the effect of this temperature increase that is the more significant, the largest, Basha, in gases, but still, even if the temperature increases or the speed increases by this much, is it still enough to reach these two speeds? No. Right? So remember this. The speed of sound that is the fastest in solid and then the slowest in gas. But if we increase the temperature of each one of these by the same amount, Basha, you can see that the speed of sound increases, Basha, more in gases, Basha, because of the temperature change. But once again, even if you add this increase to the total, you will not get to the same speed as those that are like, it is true that speed of but still not enough to reach the speed of sound in solid or liquid. So remember this, because this is something very important. All right, that is the effect of temperature in these, we can say, states or mediums here. So once again, Gutman, sound waves can travel through each one of these mediums, solid, liquid, and gas. Solid, because the particles are close, so the energy transfers very quickly. It can go from one particle to another, so it is the fastest. It is slower. It is the slowest in gases here. So now we have this question also says, what does the speed of a sound depends on? It depends on two things, Basha. It depends on, the first thing, it depends on how fast these particles transfer their energy, or this sound wave in this case here, from one particle to the neighbor particle, because the faster they transfer their energy, right, we can say the faster the sound. And this, of course, would be much more faster if the particles are close, because you don't have to go that far, right? So the faster you go, let me give you an example. Perhaps, let's say there's, God forbid, a fire when you, and everybody in class, let's say you guys are lining up to help, like let's say extinguishing the fire and all of that, right? Imagine if one person is over there and you're here, and then there is another person there. You have to carry the water. Let's say we're using water. You have to carry the water. One person has to carry and travel, walk that long, and then give it to this person and then to the next. But what if there are a lot of people, for example. Now this, of course, water can be transferred, like one person can hand it over to the next, and then that can, of course, the water can be delivered way faster, and this is exactly how it works in solids, liquids, and gases. Basha? The speed of a wave depends on how quickly one particle can transfer its motion, its energy to another particle. Right, that is the first thing. And also the second thing is the temperature. Gutman, once you increase the temperature, the particles vibrate faster. So this faster vibration makes the particle to transfer the energy from one particle to another way faster. And then this is how sound energy, or let's say temperature, can affect the speed of sound. All right. This table, Bob, you don't have to memorize this table, but just remember, if you need a number, if the question is ever asking, we can extract it. We can extract it here. Okay, and you can see that, for example, if speed of sound in gases in air, if at 0 degrees Celsius is about 330, at 25 it is about 340, Basha. And you can see that once the temperature increases, it is about this much, and these are different gases. But if you look at liquid at 25 degrees Celsius, right, for example, seawater, sometimes we use this one, which is about 1,530, roughly about, we can say 1,500 Basha. And then, but these are solids, for example, aluminum, copper, iron, lead, or let's say, I don't know, what is the rubber, basically, Basha. So in aluminum or copper, you can see that it's about 5,100. The other one, for iron, it is 5,130 and all that. It is, we can say, for solids, it's roughly approximately around 5,000 meter per second, which that is pretty fast, of course. All right, now another question says, why is the speed of sound as fastest in solid? Yalla. Gutman, the speed of sound is the fastest in solid because the particles are very close to one another. So one particle can transfer its energy to the neighboring particle very quickly. Of course, that makes it go faster compared to liquids or solids. Bash, another question says, explain why the speed of sound depends on the temperature of the medium. All right. And then also the second part says, why is this temperature dependence? It is more noticeable in gas than in solid or liquids. And we said that, we've explained that. We said as the temperature rises, the kinetic energy of the particles increase. When that makes the particle to vibrate more frequently, to vibrate faster, let's say. That faster vibration allows the energy of a particle to be transferred from one to the other one very fast, or you can say quicker. So that makes the sound to travel faster in that medium here. And why is that temperature dependence more noticeable in gas? This was Rosati, you can say. This temperature dependence, it is more noticeable in which one of the following? Is it gas, liquid, or solid? Because solids are pretty close to one another, so even once you increase the temperature, they cannot travel or vibrate that much, right? Because they're bound here. In liquid, they can vibrate a little bit more, so it can increase a little bit more compared to solid. But in gas, because the particles are very far, so now once you increase the temperature, they can vibrate or you can say much more now. And the faster the vibration now, of course, the faster the speed of sound. That is why this temperature dependence, it is more noticeable in gases. But man, this allows the disturbance or waves to propagate, to transmit faster at higher temperature. Good man, in liquids and solids, the particles are already close enough together so that the difference due to the temperature change is very, or you can say it is less noticeable. Yalla Baba. We have another question, says, if the wavelength of a sound, like how do you solve questions like this? If a wavelength of a sound is reduced, remember, by a factor of 2, what happened to the wave's frequency? Am I good man? Frequency and wavelength are inversely proportional one, yeah? So if not, it would be even better if you just write this equation here. Frequency times wavelength. Good man, whichever or by whatever the factor something reduce, you just take the reciprocal of the other. Basha, this one says the wavelength reduced by 2. Yani wavelength ka beta 1/2. And the frequency ka, by what factor will it change? You just take the same fraction but do the reciprocal. That is going to be 2/1. In other words, the frequency increases 2 times. Basha, the second part of the question says what happens to the speed? Basha, isn't this the same medium? Yes, Kata, speed remains the same. Don't forget that one. Okay, next says, as a result of a distant explosion, an observer first senses a tremor, Basha, first senses a tremor, which is a vibration that you feel, for example, once it is passing through the ground, Basha, then here's the explosion. What accounts for this time lag? Basha, let's say there is a distant explosion, Basha, it is far from you. First, you feel the ground shake, which we call it the tremor, or the vibration through the ground. First, then later you will hear the sound, or some time later, all right, then you hear the sound. Why the sound is this late, this lag, Basha, or what causes this lag? So of course we said, because this vibration is passing through the ground, and the ground is solid one, yeah? So can we say sound travel faster through solid? Yes, this is why we first feel the vibration, then we hear the sound from the air. That is because sound travels slower in air. Don't forget that. Okay, the next thing that we have says, the range of human hearing extends from approximately 20 hertz to 20,000 hertz. Basha? So the question says, find the wavelength of these extremes. What does extremes means? That means these ends, Basha. So don't forget this. Extremes here represents the ends, Basha, or the edges, you can say. Extremes when the speed of sound in air, it is equal to 343 meter per second. Yalla Baba, remember this. Let's write what is given here. So we have the first frequency. We can have the second frequency. Basha, the first frequency, it is 20 hertz. That is for human hearing, yeah? Or hearing range. The other one is 20,000 hertz, right? And then the speed of sound, it is 343 meter per second. Now look, we've learned that frequency and wavelength are inversely proportional, yeah? So how about if I should have, like drawn this one here, this way. Okay, so this is the first frequency. And then this is the second frequency, which is equal to 20,000 hertz. And then the speed of sound, all right, it is in each one of these, no matter what the frequency is, it is the same, which is 343 meter per second. And this is, for this one also, it is 343 meter per second, Basha. Now, Basha, if I have frequency and speed, can I find the wavelength? Yes, but this wavelength you find, it is going to be the first wavelength or for the first frequency. Now, you also know that if the frequency is low, obviously the wavelength it is going to be long, Basha, or long here. This frequency is higher, got that the wavelength will be shorter. Remember, we'll use high and low for frequency, long and short for the wavelength. All right, so in this case, wavelength, the speed over the frequency, which in this case, the speed is 343 divided by what? Divided by 20. I think that is 70 something, right? If not, we'll use a calculator. 17.2. So the wavelength that is going to be 17.2, that is going to be in meter. Don't forget, that is, we can say, the first wavelength. But what about the wavelength for the next one here? Can I find a wavelength here? Yes, you can call that second wavelength. Again, speed over second frequency. Speed is 343, but this time divide by 20,000 hertz, right? So in this case, it is going to be what is it equal to? It is 0.0172. 0.0172, that is a wavelength, so which is going to be in meter. So now these are the wavelength, Basha. Remember, we have frequency and a speed, so you can find the wavelength. Frequency and speed, because this is the same medium, so the same speed. So we can find two wavelengths for the lowest frequency and for the highest frequency as well. Basha, this question is pretty much easy, and of course it's interesting too. We have another question. This is also something else, and there is an idea regarding this one, and there is also, we can reverse this question too. It says, a dolphin at 25 degrees Celsius seawater emits a sound directed towards the bottom of the ocean, which is 150 meters below. Can I say this is the depth of the ocean here? So you can see that this is the dolphin here, emits a sound, the sound that is going towards, or let's say to the seabed or to the bottom of the sea. But how far is the bottom of a sea? It is 150, Basha. How about if we just do that here? So this is the surface of the water, okay? And so the depth of the water is 150. So a sound is sent, all right? And then after the sound hits the bottom of the sea, and then it is going to be reflected and it comes back. So the question all right? The question says what? How much time, that is delta t, passes before it hears an echo here? Now, let me ask you something. For the echo to be heard, or when exactly do we hear the echo? The sound has to go all the way to the bottom of the ocean, and then it needs to come back as well. Once it comes back, then of course it can be heard by the dolphin here. So, but here's my question. In order for the echo to be heard, how far does the sound has to travel? Can I say 150 down, right, to reach the bottom of the ocean here, and then or sea, whatever that we have, and then it has to travel 150 up so that the echo can be heard. So what is the total distance traveled by the sound? Now we can say it is 300. If not, you could just call it 2x. Basha, Kawata, remember this velocity here, it is equal to delta x, that'll be the distance, divided by delta time. But remember, if you want the time or the echo time here, Basha, echo time, so let's just say echo time here. Remember, in order for the echo to be heard, all right, so this distance that we have, it needs to be multiplied by 2. Why does it have to be multiplied by 2? Because one's for going, because if the sound is only going, you're not going to hear the echo. In order to hear the echo, it has to go all the way to the bottom and then come back, then you can hear the echo. Basha? But if it is traveling, so that is going to be 2 times the distance, 2 times 150, that is going to be 300, you can say, divided by the speed of sound in water or the ocean here. So 2 times, remember, 150, that is the distance, divided by the speed, which is 1,530 meters per second. Once you do the math, of course, you'll get what? You'll get 0.2 seconds here. Okay, you can make this 130 if you're willing to. All right, so now this is how much time it takes before, or let's say for the echo to be heard. Basha? Okay. Now, once again, why do we say 2x? Because the question says find the echo time. Basha? It says echo time. The question says find the echo time. Basha, what if the question is not saying find the echo time? In that case, that'd be just 1x. That'd be like how long does it take to reach the bottom of the ocean? All right, that's a side one, yeah? How can we change this question here? We could reverse the question. What if the question gives you the echo time, which is 2 seconds? All right, echo time, which is 2 seconds, or 0.2 seconds. And then it tells you the speed of sound in water, it is 1,530 meters per second. What if the question says or asks, what is the depth of the ocean or the sea here? All right, it says what? A dolphin seawater, yes. So what if the question says, what is the depth of the seawater? Don't forget the depth of the seawater. So what exactly do you do? All right, you of course have two choices here. This time that we have, it is the echo time. That means the time for going and of course for coming back as well. Basha, if I want the time only for going, can I just divide this time by 2? Yes, so if you divide this time by 2, right, then of course you get 0.1 second. That'll be only the time to reach the bottom of the ocean. Basha, now at this point here, if the question says what is the depth of the ocean, we can say V decata delta X over delta T. Basha, but this delta T is not echo time anymore because we want delta X. Delta X would be V times delta T here. Like, how far does the sound can travel in 1 second? So it's going to be 343 times 0.1. So of course you can find the depth of the ocean or the sea here, which is going to be about 150 meter. Basha, a little bit less or more doesn't matter. You can use a calculator. I think it's going to be a little bit, not precisely 150. Let's see what exactly equals to. 343 times 0.1. The answer is going to be 343 times 0.1. Okay, it is equal to 34.3. There's something wrong, I feel like. Okay, we have echo time, and we have... what did I do? I'm using the speed of sound, dude. Okay, so remember, speed of let's say sound in water, it is 1,530 times 0.1. Basha, 0.1. So let's do that. 1,530 times 0.1. The answer is 153. Basha. So 153. This is meter, or in meter. This is how deep we can say the sea is right at this location. So once again, but when do we do this? If the question is ever asking you to find the depth of the water and they gave you the echo time. Remember, the echo time, that'll be the time for going and then coming back. Basha. So we just divided the time by 2 because that'll be only the time for going here. Then you could easily do this. There's another method you could do that. You could have found the distance here, Basha, by using the echo time, but at the end, this distance you find that is going to be for going and for coming back, you could have divided the distance at the end. And if you don't divide the time by 2, at the end, once you find the distance, you'll have to divide that by 2. Why? Because that'll be the distance for going and coming back to the surface there. Okay, so hopefully you understood the idea. It's pretty simple, but of course it is. It could be important. All right. The next thing that we have, it says sound waves propagate in 3 dimensions here. That is also something interesting or something important for Wazari too. All right. So what exactly do we have now? When we have sound waves, okay. When we have sound waves. When I talk, for example, to you, or if you're in a class or somewhere, the sound spreads in all the direction or in all the directions equally. So we'll say sound spreads in 3D or 3 dimensions, right? Is it just forward or to the side? No, it is. Imagine you're inflating a balloon, right? The size of the balloon increases in all the direction. This is how the sound spreads, or you can spread, Basha. So if this is, like we can draw something here, Basha. Maybe we could draw some circles like this. That'd be better, maybe. Okay, but let's just move this one a little. Too late, I guess. All right. All right. So here we can say these circles represent sound waves that are spreading here. So this would be x-axis, you can say. This would be y-axis. And this is going to be you can say z-axis, right? This determines that or represents that the sound travels in all the directions here. Now, we can of course draw more arrows here. What does these arrows represent? That represent the direction of like which way the sound is propagating or transferring here. Now, what are these circles here? Now, because these are of course 2D here, so each one of these circles, Baba Agalibi, these are representing, Basha, or each one of these circles represent the center of a compression, and we call each one of these lines, we call them wave fronts, Basha. What do we call these circles here? We call them wave fronts. Wave front here. Just exactly the same as, good man, if we have ocean water here, right? Aren't these are, for example, these are the front of a wave in here, because these waves are moving forward here. So each one of these lines or each one of these circles are called wave front or the front of a wave, Basha. And you need to know that, Baba, each one of these wave front is representing the center of a compression, Basha, the center of a compression. Kata, if I draw a sine wave here for this, okay, we could do more waves at this point here. This is how it is going to be, Basha. This is not accurate. Let's make it a little bit more accurate. This is how it is going to be. So you can see that each one of these circles represent what? Represent the center of a compression here. Basha, if that is each one of these represent the center of a compression or one wavefront to another. Basha, if you wonder, for example, isn't this similar to, like for example, a crest to crest, even though these are not crests, don't forget, compression to compression. So we can say the distance between one wavefront to another, it is equal to one full wavelength, Basha. Got at any point, even if you have more circles, okay, we could do more circles if you want to here. These circles has to be symmetric and all that. That's not perfect, but okay. So we can see that the distance between one wavefront to another, it is equal to one wavelength. Another wavefront to another, right? Or from this wavefront to the other, that is also another wavelength. And remember this, the center of, or each wavefront represent the center of a compression here. So this is what it is. What about, you might wonder, what about somewhere in between the two wires, somewhere like here? That of course represents the center of a rarefaction, if it is exactly or right in between the two wave fronts. Okay, so once again, what have we learned so far? Man, sound travels, propagates, transfers in all the dimensions here. How many dimensions we have? 3 at this point here. Asha, so sound travel in all the dimensions or in 3 dimensions. Just like we said, the same as if you inflate a balloon, so it is going to expand in all the direction. That's exactly how it looks like. Each one of these circles are called wave fronts. Each wave, or the distance between one wavefront to another, that is equal to one full wavelength. Basha, what if I ask you, what is the distance between 3 wavefronts, right? How many wavelengths will be there? Of course, you might say 3 right away. That is incorrect. Whenever they'll ask you how many wavefronts are there, if possible, draw the shape, okay? And then if not possible, then there is another method that we can do. Watch this, Baba. Isn't this 3 wavefront? If we start here, 1, 2, 3, one, yeah? Good man, the distance between 3 wavefronts, how many wavelengths are there? He said 3, but it's incorrect. Let me tell you why. So because from 1 to 2, that is 1 wavelength, one, yeah? What about from 2 to 3? That is another wavelength. But on these are 3 wavefronts. Got that the distance between 3 wavefronts, Baba, it is only equal to 2 wavelengths, Basha. So we can make an equation as well. If number of wavefronts is given, Basha, to find how many wavelengths are there, Basha, to find the number of, Basha, wavelength. If the number of wavefront is given, we can say number of wavefront, Basha, number of wavefront minus 1. So for example, I said if we have 3 wavefronts, how many wavelengths will be there? I'll say 3 minus 1, that is going to be what? That is going to be 2 wavelengths, Basha. Now in Wazari, how, you might be asked something like this. The distance, right? Let's say between 3 wavefronts, the distance between 3 wavefronts, that is equal to 12 meter, Basha. What is the wavelength for this wave in here? Okay, so remember this. That is the distance between 3 wavefronts. That is 1, 2, 3. Good man. Between 3 wavefronts, you can use this or you can count yourself. That is 1 wavelength, that is 2 wavelength. So in other words, 2 wavelength, that is equal to what? right? Or if not, you can use this one here. So 2 wavelength now, we can say 2 wavelength دكاترة 12 meter. Basha, what about the 1 wavelength? That is going to be 12 divided by 2, which is going to be 6 meters. So each wavelength is now going to be 6 meter long. Okay, now there's one more thing, like regarding this one here, and that is what happened as these wavefronts spread more and more here. All right, so we said these are, you can say this is the source, all right, or the source of the sound. Then from the source of the sound is spreading. So these are the wavefronts getting larger and larger. Remember, each one of these wavefronts or these circles need to be concentric, Basha. So what happened as these, like wavefronts get larger and larger and larger here. So at some point, of course, this is how it looks like when So if you look at, for example, once we get too far from the center, how do these wavefronts look like to you here? Don't they look like as if these lines are parallel? These lines represent wavefronts too, but don't they look like as if they are parallel lines now? Aren't they approximately look like parallel? Well, the reason why, because we are at great distance from the center. So if we are at great distance from a center, then these lines that look parallel now, if you take a section, right, a segment of this lines here, they look parallel to one another, but only at great distance. Then we can call this one plane waves. What do we call them? Plane waves. But I got it. We have a chapter review question says, can we consider the innermost waves, the twanin babashaglera, that is close or very close to the center? Can we call any wavefronts here plane waves? The answer is no, because in order to call it a plane wave, it has to be very far from the center. Then it looks like parallel. Then we can call that one plane waves. Basha Baba, Agal Derabi. I believe that is everything you need to know, Basha. So the each wavefront represents the center of, or corresponds to the center of a compression. Yan, we can say represents the center of a compression. Right? Remember this? And each one of these, by the way, each ray represents a sine wave, because sound it transfers, it propagates in all the direction. In all the direction here, 3D, but we'll just of course take 3 here, and each one of these waves here, you can see that it is corresponding to a single, or each one of these ray corresponds to a sine wave here. And this is how the wave is spreading or traveling. Basha? A point 10 in the Baba. Good, the circles represent the center of compression. These are called wavefronts, Basha. And each wavefront located at the center of a compression. These are almost like similar. The distance between the adjacent wavefronts, it is equal to 1 full wavelength here. The radial line perpendicular to the wavefronts, these are called ray. These radial lines here, or those lines that are perpendicular to the circle, you can call them ray, which represents which way the sound is going, just like light rays that you've studied before. All right, 5 says, the sine curve corresponds to a single ray. Good, these are, we don't only have like one single sound that's traveling, it travels in all the direction. So these are, like each one of these can represent a sine wave. And we also said that these wavefronts are very far from the center here. You can see that. Spherical wavefronts that are great distance, maybe you can underline this part for yourself. These waves that are at great distance, right, from the source, okay, from the source can be approximated with, we can say, parallel lines. Only if they are at great distance, then we can call them plane waves. Basha, plane waves can be treated as one-dimensional wave at all traveling in, because all of the waves will be traveling in the same direction. Good, Baba. Only if we're talking about, or only if the number of wavefront is mentioned. To find the wavelength, we can say wavelength and the number of wavelength. Let's say how many wavelength we have. You can call this a number of wavelength, Basha. The kata wavefronts that are given -1, that'll be the number of wavelength that we have. For example, the question says there are 12 wavefronts. How many wavelength are there? Or the distance of 12 wavefronts, the kata 10 meter. What is the wavelength of one? Then you can use this equation, then you can find the answer. Yalla, we have this Wazari question 2 says, the distance between adjacent wavefronts of a sound, what is it equal to? Gatman, it is equal to 1 wavelength. All right, the next thing that we have is breaking sound barrier. What exactly breaking sound barrier is, Baba? Now, we know that. Let me give you some, perhaps, idea about this one. For example, now, when you walk and talk, because you're the speed of sound that is obviously faster than you if you're just walking. So your sound will be going ahead of you, yes or no? And then you would be just following the sound because your speed is less than the speed of sound. But what if you're inside a plane, Basha? Okay, so at a point here, so we're talking about breaking sound barrier. What exactly is this? Imagine this is a plane, Basha. Okay, and we're not getting drawing planes, so I don't know, maybe this. Okay, so this is a plane. If this plane is at rest, right, the engine is on, the sound will transfer or propagate in all the directions equally. And of course, watch this, Baba, when these, for example, circles are, like in each side, if the distance between each one of them are equal sized, yani, the sound travels in all the direction at the same speed or equally there. But so this will be the direction of sound propagation for a plane that is at rest, velocity 0. Basha, what happens if this plane starts to move? Okay, once again, but at this point here, if the sound, if it is not moving that fast, okay, so we can see that the sound is traveling or going ahead of the plane here, but now the plane is trying to catch up in here. So at some point here, or this side here, you can see that that's not a perfect diagram, but the point is this plane is going forward, right? The sound is ahead of the plane, you can see that. So can I say the speed of the plane, it is smaller than the speed of sound? Yes, because you can see that the sound, these are wavefronts, okay, which are going ahead of the plane, of course, which means that the speed of the plane is less than the speed of sound. Now, what happens if this plane decides to speed up? At some point where the speed of the plane, right, matches the speed of sound. In this case, of course, something interesting will happen. So this is, like you can say these are the sound waves here. Now, because these two are having the same speed, so the sound is trying to go ahead of the plane, but because the plane catches up right away here, so we can see that all these sound or wavefronts, sound waves, all of them are combined right at this point here. And once this happens, it forms something like a barrier here, Basha. And we call this one sound barrier. What do we call this? Sound barrier. But now here's the thing. When will sound barrier be when will sound barrier be formed? What am I saying? All right. When will a sound barrier or sound barrier will form? When will a sound barrier will be formed? Will be formed. Okay. So at this point, you can see that all these sound waves are so at this point here, all these sound waves or wavefronts are piled up together. We call that a sound barrier, Basha. So there will be a question, of course, when will a sound barrier will be formed, Basha? We'll say the sound barrier will be formed when the speed of the plane, Basha, matches or equals the speed of the sound. Okay? Once these two are equal, then once again, the speed of or the sound tries to go ahead of the plane, but the plane catches up right away. So you can see that these two are having the same speed in here. So produces or produces this barrier here. We call that sound barrier. But this is not a safe situation. This situation is critical, and it is not safe for the plane to stay at this speed. Why? Because these are too much pressure. And we said that sound waves are caused by vibrations, so it would produce different regions of, let's say, compressions and rarefaction. So we imagine all these compressions, Basha. So this makes the plane to vibrate, Basha. And of course, it is not safe for the plane to stay at this speed. So it is either has to speed up more than, increase its speed or slow down a little bit to, for example, avoid being at this state right here because it is not safe. So what happens if the pilot decides to speed up more than a little bit more or even more than that? In this case, of course, Baba, this barrier now it is going to be broken, Basha, because this plane now it is going penetrating through the barrier, so this barrier will be broken. As it is broken now, what exactly will look like? So now at this point, it is going to form something like a cone shape in here. So these would be Basha. This would be now, we can say, the shape of the sound that is produced now. So the plane is going ahead, but now the sound is, we can see that it is left behind, or it is spreading behind the plane. And as you can see here, we can see that these ripples are formed at the edge of the plane. That is totally fine. Okay, so at this point we can see that the speed of the plane will be faster than the speed of the sound. Basha, speed of the plane, it is greater than what? Greater than the speed of sound there. So the sound, of course, would follow the plane there. So let's summarize this one more, and then of course we're going to add a little bit more detail into this. Gutman, if the object is now moving, the sound spread in all the direction equally. Basha, what if the plane is moving, but the speed of sound, these are not perfect diagrams, but okay. Let's say this is how it is going to spread. Let me just redraw this one here. Okay, so good man, this is how it is. At one side is closer. Wow, Alice says this is supposed to be better than the last one. Okay, this and then this one, this is how it is going to be. So you can see the wavefronts are closer. That means the plane is moving in this direction. And these side is getting further apart. That means these are, of course, moving away from this side. So this is how it is moving forward. But once again, the plane is moving away, so we can say disturbance are produced. What exactly are disturbance about? A sound wave. Sound waves produce regions of compression. Let's say there are compression regions and rarefaction regions. These are disturbance that are passing through the air. Basha, that is for this one here. And then at this point here, good man, when the speed of the plane increases, matches or equals the speed of the sound, then sound barrier will happen. And also there is something else. There will be a shock wave formed as well. What is a shock wave, Baba? Hangutman, there is an instant change in the pressure because we can see that as the speed increases, so the particles get instant pressure, change in temperature, change in pressure and density and all that. So you can call that one shock wave. Or you could just say, when the speed of the plane matches the speed of the sound, two things will happen. First, there will be a sound barrier, and also there will be a shock wave that is produced by the plane as well. But what happens when this speed of the plane exceeds, it becomes faster than the speed of sound? Then the first thing to happen, we'll say the sound barrier, it is broken. The sound barrier is broken, Basha. So there's no sound barrier anymore. And then there will also be what? There will be shock waves too here, Basha. Shock wave. Shock waves too. And then we can also say that as a result of these breaking sound barrier, there will be a large sound, the same as the explosion sound. Why is that? Because the plane has just exceeded the speed of sound. Or as this barrier is broken, that lead to a, we can say, a huge sound. And this sound, of course, if it is very close to the ground, it can break windows, let's say, or anything that is fragile or that is not very rigid. Basha, sometimes they use that in, let's say, war zones just to disturb people or maybe to do some damages there. So these are the most important thing that you need to know regarding this Baba. This, like, how will this be in Wazari? I'll tell you, this been in Wazari, I think a few times, Basha. So this is obviously the plane. At this point, it is traveling to the right. You can see that. Once it is traveling to the right, the wavefronts are getting closer here, but spreading from the other side. So that is an indication that the object is moving from the side because the sound is trying to go ahead, but then the plane catches up, so the side gets closer. And then at this point here, when the speed of the plane matches the speed of the sound, all these wavefronts, of course, pile up now. So we call this one a sound barrier, but it's not broken yet. And at this point now, we can see or we can say there is a shock wave formed as well. And at this point here, now when the speed of the plane it is larger than the speed of sound, this sound barrier, it is broken now. And also you can see that it forms a cone-shaped, we can say this cone shape, of course, indicates that the speed of the plane, it is faster than the speed of sound. So the sound waves are left behind, Basha. Okay, now this table summarizes everything that I said, Basha. Gutman, this one creates a disturbance, and disturbance there. This one, but Gutman, here, by the way, don't forget, only shock waves will form when the speed equals to or exceeds. Otherwise, when the speed is smaller than the speed of sound, the speed of the plane is smaller than the speed of sound, there will be no shock waves. Okay, and then Gutman, no sound barrier here. There is a sound barrier. There is no sound barrier because it is already broken here. And then minimal energy release. Gutman, energy, the energy that we have, that is obviously minimal because that would be just traveling through or transferring through the air. Later, Gutman, it forms a sound barrier. So there's maximum energy or pressure on the tip of the plane. We said it is not safe for the plane to stay at this speed here. Then this one, of course, that also produces, we can say, extreme amount of energy will be released at that point there. So Gutman, high energy buildup at the nose, which is risk of instability, and then extreme energy release that can shatter windows, of course, or damage the other structures, you can say. All right, these are, of course, the repetition of what we just said, but just remember one thing, Baba. Breaking the sound barrier by a plane gives rise to a huge amount of energy that might break window panes or window panes or pane, whatever, and sometimes Basha. And this diagram, Benin Wazari Baba says, which one of these diagrams indicate or show that the speed of the plane is larger than the speed of sound? That would be this. What if next time says, which one of these indicate that the speed of sound that is less than the speed of the plane is less than the speed of the sound? That would be this. Which one of these indicate that the speed of the plane matches or equals to the speed of sound? That is going to be this one right here. But what if we say, which one of these indicate that, Basha? All right, which one of these cases shock waves will be formed? That'll be both B and C here. Okay, which one of these we can say the speed, we've mentioned that when the speed of plane is faster than the speed of the sound. What if it says which one of these, the speed of sound, just the same question but reverse, which one of these show that the speed of sound is less than the speed of the plane? That will also be option C here. Now, remember this, Gutman, shock waves are generated, that is a steady tip, very important. Now, shock waves are generated in both cases, when, like these two cases, when the speed of the plane matches the speed of sound, and also shock waves will be formed when the speed of the plane it is bigger than the speed of sound. But breaking sound barrier only happens when the speed of the plane it is larger than the speed of the sound. And of course, once the sound barrier is broken, sometimes we call it sonic booms, Basha. So because it is, or there is a huge amount of energy release, and that of course sounds very, very loud. Okay, the next thing that I want to talk about is Doppler effect. Now, Doppler effect is something that we experience every day, Basha. So what is exactly Doppler effect? If you remember the other time we were talking about this when we were talking about pitch, Basha, Gutman, you're standing here or at a corner, doesn't matter, on a street, Basha, you walk in, then you hear or you see an ambulance, like coming towards you. While it is coming towards you, if it is sounding, it is siren here, you will notice that the sound of the ambulance gets higher and higher and higher until it gets or passes you. And then after that, after it's moving away, the sound gets lower and lower and lower. So you feel there is a change in the frequency that you hear. When there is that change in frequency that you hear, or that change in the frequency you hear, we can call that pitch, if you remember. So why is there a change in bubbling frequency that you hear? That is because of something that we're going to call it Doppler effect. Basha, Kata, what is Doppler effect, Baba? We'll say it is a shift, it is a change in the frequency that we hear, Basha. And what is the frequency that we hear? We call that pitch, Basha. And why is there a shift in the frequency that we hear? Because there is a relative motion. Kata, we can say Doppler effect, it is a shift in or a change in the frequency that is observed due to a relative motion between the source and the observer. Remember this, Doppler effect happens with all kind of waves, Basha. So once, don't forget this. And also it happens as long as there is a relative motion. Basha, if there's no relative motion, there will be no Doppler effect. And in what case we have no relative motion, Baba? If the object that is producing or making the sound, and if the observer, like a person, if these two are both at rest, there is no relative motion, obviously, because these are stationary. What if both of these are moving with the same speed and same direction? In other words, they don't get closer or further. If they're moving, but they're both moving with the same speed and same direction, because the distance between the two doesn't get any closer or further, like the distance doesn't get any closer or further, so we can say there is no relative motion as well. In that case, also there will be no Doppler effect. So when we say no Doppler effect, you will hear the same frequency as the frequency of the source. But if there's Doppler effect, you will either hear a frequency that is higher than the frequency of the source, or a frequency that is lower than the frequency of the source. So when do you get higher frequency, Baba? If there is an approach between the source and the observer, like the ambulance and a person. If they approach one another, then we'll hear, or the person will hear, a frequency that is higher than the frequency of the source. We call that pitch, Basha. And then if they are moving apart, away from one another, then the observer will hear a frequency that is lower than the frequency of the source. Also, like for example, once we say if there is an approach, right, it doesn't matter which one is getting closer to the other one, as long as they're approaching. It could be the ambulance getting closer, the person standing. It could be the person moving towards the ambulance. They could be both moving towards one another. These are all valid situations here, right? So al-muhim, as long as they're getting closer, which one is getting closer doesn't matter. As long as there is an approach between the two, there will be, or the frequency that is heard will be higher than the frequency of the source, Basha. If they're moving away from one another, the frequency that is heard will be less than the frequency of the source. How's it, Tamasha? This diagram, Baba. All right, so we have this ambulance that is getting closer, for example, to this man, and then moving away from this woman here. Okay, so now, because it is getting closer to this person, you can see that. So this one, of course, each one of these circles represent a wavefront one, yeah? So you can see that the frequency that this man is going to hear, it is going to be higher. More up and down, that means higher frequency, Basha. So the frequency that is heard by this person, that is going to be higher, the frequency of the source, but also the frequency that this man, it is going to hear, will also be higher than the frequency of this woman, because this ambulance is moving away from this woman. You can see that there is less up and down, so you can also see that the wavelength is long. If the wavelength is long, frequency and wavelength are inversely proportional, when yeah. If the frequency is low, of course the wavelength, and here it is vice versa. Al-muhim, Baba. If it is approaching, the frequency that is heard or observed will be higher. If they're moving away, the frequency that is heard or observed will be lower, Basha, and that is what you can call Doppler effect. So what is Doppler effect now? We can say it is the observed change, Basha. It is the relative change. It is the shift in the frequency that is heard, Basha, or the observed change in the frequency when there is a relative motion between the source of a wave and, of course, an observer, Basha. An observer, it could be a person, Basha. It could be a device that can sense the frequency, Basha. Okay, so, but in most of the cases that we have, an observer is a person, Basha. Okay, the observer will be the person who hears the sound or who can detect the sound, Basha. With my few study tips or a few notes about Doppler effect, Baba, previously we said frequency determines pitch. That Doppler effect affects the pitch that is heard by Babylon, by the person. Doppler effect, Jan Babylon, frequency of the source, Baba, will never change. The thing that will change, it is the pitch, it is the frequency that you hear, not the one from the source, Basha, because from the source produces a certain frequency, let's say 10 hertz. You, as an observer, you might hear like 12 hertz, Basha, right? So this extra or frequency that you hear, that is a pitch, Basha, that is not from the, what is it called? The source is still producing 10, but you might hear either a little bit higher or lower. That higher, lower, you can call that Doppler, or it is caused by Doppler effect, Basha. So remember, the frequency of the source does not change. It is the pitch that you hear will change. That is first. And then, or you can say this one, the observer in the front, that is the regarding the diagram, which no need here. Point number 3 says Doppler effect occurs in all waves, including electromagnetic waves such as visible light as well. And I need you to underline this one too. And I think it's been in Wazari once. It says Doppler effect occurs in which one of these? Is it just sound waves, electromagnetic waves, visible light, or all of them? In that case, you have to choose all of them. It is not just sound or light. It is all kind of waves, we can say. Basha, what is the equation of Doppler effect? Or what exactly how do we use this equation? At this point, perhaps you need to pay a little attention at this point, Baba. So this is the frequency. You can call it f prime. This is the observed frequency, Basha, or the frequency that is heard by the observer. Observed frequency. It is equal to frequency of the source, Basha, multiplied speed of sound in air, Basha. Speed of what? Speed of sound in air. Let's say sound in air. All right. There is also, we can say plus minus, Basha, and then speed of the observer divided by speed of sound again in air. Once again, plus minus speed of the source in here. Okay, but hereafter, we're not going to write all this, Basha. So this is the main equation that we have. Don't forget, this is the main equation that we have. Hereafter, we're just going to write this instead, Basha. Let's say f prime, that is the frequency of the observer, or the one that is observed. It is equal to frequency of the source, v minus v observer, v minus v source, Basha. And of course, we can write a bracket in here. And then this would be for the source as well. You might say, Mr. why aren't you writing positive and negative? We're just going to keep it negative or minus here because we'll do some calculations. This format will make it easier, Basha. So, but don't forget, these are speed of sound in air. These are always the same to one another, Basha. This would be the speed of the observer. This is the speed of the source in here. So how do we, for example, finalize this one, Baba? Like in calculations, how do I know which one? Because this is the main equation, Basha. So it could be positive or negative. For example, v, or speed of sound in air, it could be plus v observer or minus v observer. This one is the same. So how do I know when I choose positive and when I choose negative? Let me tell you this. First of all, you need to use this equation right here. Okay, how about we just clean this one here? Consider an ambulance, okay, moving towards an observer. Or it could be an ambulance and observer. We said that the direction of a sound, it is always directed towards the observer, no matter where the observer is. This is the direction of a sound. So if the source is there, the observer's, let's say, to the right, the direction of a sound is going to be to the right. What if the observer is to the left? Okay, if the observer is to the left, then the direction of a sound, that is going to be what? It is going to be to the left. And that is, I think it is pretty normal. It's logical too. If a car is sounding its horn, no matter where it is or where it is going, you will always hear the sound if it is close to you, of course, if it is close enough. So whether moving away or towards you, you can still hear the sound, which means that the direction of a sound that is always towards the observer. That is the first thing. So, of course, this is going to be the speed of a source, and this is the speed of the observer. So here is the main equation you need to know. Okay, frequency of the observer, it is equal to frequency of the source, speed of sound in air minus speed of the observer in a bracket over speed of sound in air minus speed of the source in, once again, in a bracket. So now the only thing you need to know is finalize or see what is the equation based on whether approaching or moving away. Then you can write these into the equation. Watch this one closely. Now watch this. If the source is moving towards the observer, all right? So always remember the key. We have to compare the direction of the motion always with the direction of a sound. We've learned that in physics. If two things have the same direction, all right, it is positive. If they have opposite direction, it is going to be what? It is going to be negative. So now based on this one here, if the source is moving, approaching, moving closer to the source, these two, remember, this is the key, Basha. We always compare the direction with the key. So if it is moving closer to the observer, you can see that these are both the same direction, yes? If it is the same direction, we can say v of the source, that is positive here. But you don't write this positive into the final equation, no. You just write this positive right here. So if this is positive now, positive, positive becomes what? Positive, negative, it becomes negative. So now, instead of this 2 here, you could just write negative. That is for what? For velocity of the source, Basha. Now, that would be the final answer. I don't like to do this one here. I like to keep this one there. I'll write whatever I get inside the bracket, then that would be the final answer. In this case, we can say V, and then, or frequency of the source, V over, let's say V, Gutman, positive, negative, the beta, negative V source, Basha. That is if the source is moving towards? Basha, what if the source is moving away? Don't forget. Now, let's go back to this. We'll erase this one now, Basha. If the source is moving away, we'll erase this one too. If the source is moving away, guess what will happen? So now, if the source is moving away, this will be the direction of the source, correct? Now, compare this with the direction of the sound. Are these two the same or opposite? Opposite. So this V, it is going to be what? V source is going to be negative now. But once again, this is not the final form. You have to put this negative into this equation. Now, negative becomes what? It becomes positive. So we can say, now this one here, if the source is moving away, it is going to be V plus V source. Masha? This is how we can finalize the direction for both the source or the observer. Now, the next thing is going to observer. Now, watch this, Baba. So now we've learned that if the source is moving towards, it is going to be positive, but you just put this positive into the equation, Masha. So let's erase this one more time. All right, and then repeat this one again. Come on, if these two are both, if the source is moving towards the observer, these are same direction, so velocity of the source will be positive, but this positive, you will write that into the bracket, then you will finalize the equation. Don't forget. That is if it is approaching. What if the source is moving? This is the source. What if the source is moving away? Good man, these are opposite direction, so velocity of the source will be negative, yes? So if it is negative, on this, if it is negative, now we'll write a negative here, then you can finalize this to negative will be positive over there. So this is how we can find the direction, let's say, of, or whether it says positive or negative. Now the next thing that is left is for the source in here. Okay, let's move the source a little bit away so that we can have enough space to write the direction. The first thing, if the source is moving towards the observer, watch the towards the source, Baba. If the observer is moving towards the source, compare the direction of the motion of the observer and the sound. Are these the same or opposite? Opposite. So if it is opposite, V of the observer is going to be negative, but you bring this negative right into the equation. Negative becomes what? The final it is going to be positive here. So we can say V plus V observer. When does this happen? If the observer is approaching the source in here. Now, what if the observer is moving away from the source, right? Moving away, and getting further from the source, right? It doesn't matter. Even the source could be moving towards the observer too. Al-Muhim, the observer is trying to move away from the source. Okay, what will happen, Baba? So let's erase this one again. All right, and then this one too. So now this is velocity. If it is moving away, if it is moving away, these two are same direction, or it will be the same direction. Got the V observer, it is going to be positive, but this is not the final thing. You'll just write a positive here, positive, negative, it is going to be negative now. So V minus V observer, then divided by whatever that is below. Basha, this is how you can get the directions right. So now what is needed, or what is the most important thing, Baba, are these directions here. This is the main equation. Don't forget, okay? But man, this is the equation that you need to have. All right? And this V source, always use these brackets, and these are negative here. Then you will find which way it is moving. If it is the same as the direction, it will be positive. But whether positive or negative, you put them in brackets, then you will finalize what would be the final sign for the velocity. Then you could do the calculation. All right. Now, this is how you can do that, of course. Soon you will see that once we're going to do some numbers here. All right, remember this study tip says what? The frequency of the source does not change at any case. Don't forget, it is only the frequency that we hear will change, and we call that frequency pitch. Don't forget. Okay, so only the pitch that we hear will change. Remember, this is the equation. But man, you always, if you don't have these brackets, write these brackets, because they make it very easy actually to solve this question here. And also, remember this study tip says if the direction of the observer or the source that is the same as the direction of the sound, then we can say, or the direction of the observer or the source that is the same as the direction of a sound travel, their velocity will be positive. If not, they are negative. Now this table, it tells you what I've just said earlier here, and you can draw this diagram for yourself too, just to remember, because it might help. On direction of the sound that is always directed towards the observer. All right, good man. If this is the source, if it is moving closer, it would be positive because that would be same direction. If it is moving away, let's change the color. If it is moving away, this is going to be negative because these two will be opposite direction. If this is moving or getting closer, that is going to be opposite, so this is going to be negative. But if moving away, it is going to be the same direction as the sound, so this is going to be positive. All right, so and this is where it comes from. So you can see that for the observer, if it is moving closer, it is negative. If it is moving away, it is positive. For the source, if it is moving closer towards the observer, it is going to be positive. If it is moving away, it is going to be negative. This is how you can finalize the signs. And then after you put these signs into the equation, then of course you could finalize the signs. Now these study tips, I would rather to go through them after solving a question, but let's just go through them here at this point here. But sometimes in questions, they might tell you an observer at rest. If it says the observer is at rest, what is the velocity of the observer? 0. What if the source is at rest? That is the same thing. The velocity will be 0. And now we also mentioned that if there is an approach between the source and the observer, we'll hear a frequency that is higher than the frequency of the source. Basha, if they are moving away, then the frequency we hear is going to be lower than the frequency of the source. But now, watch this. Okay, so good man, if the frequency that is here, if it is larger than the frequency of the source, or if you write this as a fraction, it is going to be what? The frequency of the observed frequency, if it is larger than the frequency of the source as a fraction, if it is larger than 1, then we can say the source and the observer are approaching one another, Basha, or getting closer. Because Basha, we've learned about frequency and wavelength relation. They're inversely proportional. If the frequency we hear, if it is higher than the frequency of the source, what about the wavelength that we get, or the wavelength of the sound that we hear? If the frequency is higher, got that the wavelength must be what? Must be shorter. Okay? All right, what about point 4 says, if the frequency that we hear, if it is less than the source, or as a fraction, if it is less than 1, then the source and the observer must be getting away from one another. As Basha, if the frequency we hear is less, Kata, what about the wavelength that we hear, or the wavelength of the sound that we hear, that has to be longer than the wavelength of the source. And also point number 5, Baba, watch this. If the frequency we hear it is the same as the frequency of a source, all right? Or if we use as a fraction and then we get 1, that means both the source and the observer both must be at rest, or they must be both moving with the same speed and in the same direction too. In other words, there must be no relative motion. Zohar Basha. And of course, if frequencies are the same, the wavelength will be the same as well. All right, point number 6 says, remember, Doppler effect does not happen or does not occur if the observer and the source have the same speed and in the same direction. Remember, we said there must be a relative motion. No relative motion, there will be no Doppler effect. Let's jump to point 8. Says Doppler effect occurs as long as there is relative motion. That is pretty much the same idea. Point number 7, if we go back, Gutman, the direction of a sound that is always towards the observer. Now we have another question. Says you are at a street corner and hear an ambulance siren without looking. How can you tell, or how can you tell when the ambulance passes by? But previously we've mentioned this. Gutman, as the ambulance approaches, it is getting closer, right? So the frequency of the sound that we hear, it is going to be higher than the frequency of the source, so the pitch will be higher. But what happens as the ambulance passes by? Now the pitch that we hear, it is going to be lower than the frequency of the source. And you can say the frequency of the observed frequency is now going to be less than the frequency of the source. But you know that the frequency that we hear, it is called pitch. Only the pitch change, by the way. The frequency of the source will not change. Zohar Basha. I believe that'll be it for this session. Next time, inshallah, we'll solve some question. Maybe we can solve this one. We'll solve this question, by the way, or we'll answer this question. Next time, we'll turn this question into a math problem, and then we'll solve this one too. But let me just give you an idea regarding this one before ending this session. It says, a fire engine is moving at 40 meters per second, sounding its horn. And there is another car in front of the fire engine is moving at 30 meters per second. Basha? In the same direction. So there's this fire engine moving at 40 meters per second, Basha, in a straight line or on a straight in here. There is a car in front of that, Basha, this car, but this car is moving with a speed of 30 meters per second in the same direction. So these two both are in the same direction. And also, there is a van in front of the car is stationary. So there's also a van, Basha. Just for the sake of Baba understanding this better, I brought this to like side by side. Otherwise, this van is in front of the car, Basha. That's what the question's saying, but perhaps makes it easier, to compare the two or to answer the question. So I brought them back, by the way, like side by side so that you understand better. For some of your Malzama booklet, the van might be a little bit ahead of this one, but it makes no difference. All right, so it says, which observer hears the fire engine horn at a higher pitch, Basha? The driver of the van or the driver of the car or the driver of the van? Basha, without doing any math, how do we know which driver hears a higher pitch? Basha, good man. Watch this. There's this fire engine that is traveling or moving at 40 meters. There's this car that is moving with 30. And then there's this van that is at rest. There's a driver here as well, of course, right? The question says, which one of these two drivers, the driver of the car or the driver of the van, will hear a higher pitch or higher frequency, Basha? So how do we know, Baba? First, think of a relative motion. If I ask you, right, which one of these two drivers, the fire engine, it is getting closer the fastest? It is approaching these two both together, but as it is approaching this driver or the car is moving away. Kata, can I say it is getting closer to the driver of the van because it is at rest? Yes, and if you want to find the relative motion, Baba, between these two, that is going to be 40 minus 30. It is going to be 10 meters per second. This is how fast this approaching this one. But how fast is it approaching this one? 40 minus 0, it is going to be 40 meters per second. So it is approaching this driver of the van by 40 meters, like every second. So it is getting closer to the driver of the van faster. So can I say the faster approach? Yes. If it is getting or approaching the driver of the van faster, that means this person or this driver will hear a higher pitch compared to the driver of the car. Next time, inshallah, we're going to turn this to, as a matter of fact, why next time? Let's just do that now. Next time we'll go to something different. Okay, so let's turn that into a question. And by the way, this has been in Wizari as well. Okay, they've turned that into numbers. For example, let's say the driver or the fire engine has a frequency. It could be any frequency, by the way, Basha. In Wizari, I think it was 1,000 something. But it doesn't matter. So here it has a certain frequency. The speed of sound in air, Basha, it is, let's say 340, Basha, meter per second. And then Gutman, the speed of the fire engine, or the speed of the source in that case, it is going to be 40 meters per second, Basha. And now we have two cars, Basha. One of them is a van, and the other one is the car here. So speed of the van, we can say, let's start with the car. It is 30 meters per second, same direction. But speed of the van, or the driver of the van, in this case, it is 0 meters per second. So which one of these will hear a higher frequency, Baba? So let's draw the diagram again, right? So this is the fire engine. And first, let's start with the car. Okay, this is the car. This car has a speed of, that'll be the observer, 30 meters per second. But it is moving the same direction as the fire engine. But once it is sounding its horn, Gutman direction is sound, Baba. It is always what? It is always towards the observer. This is the direction of a sound, and that is the key where you compare. Now, what is the equation, Gutman? Frequency that is observed, it is equal to frequency of the source times V minus V observer, V minus V source. These are in bracket. Yalla, Baba. Let's finalize the equation first. Now, we don't know this frequency, so we could just write it F for now. And then, what about speed of sound in air? That is 340. This is 340 here. Okay, now next, watch this. This fire engine has a speed of 40 meters per second. If it is moving towards the driver of the van, it is moving, car. Aren't these two are the same direction? Yes. So same direction, any positive, yes or no? V source is positive. But now bring this positive into the equation. Positive negative becomes what, Baba? Positive negative becomes negative. So negative. What is the speed of the source? 40. All right, next. What about the direction of the speed of the car? It is moving away, right, from the fire engine here. So moving away, you can see that these are both in the same direction. Same direction, that means positive. Okay, that is V observer. When we say observer, it is the person, the driver who is inside the car. With positive negative, that is again, it is going to be negative. But what is the speed of the observer? It is 30. Now, all you have to do, just do a math. 340, Masha, minus 30, right, divided by 340 minus 40. The answer is going to be all right, 340 okay, the answer is going to be 1.03, Basha. Got that the frequency that is heard by the driver of the car, that is going to be 1.033 times the frequency of the source. Keep that in mind, Basha. Now let's do the same thing for the driver of the van in here. So now we're going to switch this with the van here. So here's the van now. Okay, so here's the driver of the van, but don't forget the velocity of the observer this time is 0. Okay, so what is the equation now? Velocity of the, or the frequency, observed frequency, or F prime, the kata, frequency of the source, V minus V observer, V minus V source. These are both in bracket. Yellow, what is the speed of the observer? 0, so you don't have to write it down. Once again, frequency, it is unknown here for the source, 340 over 340. This is out west, so 0 for the observer. The fire engine, it is getting closer to the dry Babylon van. When you got these two approaching same direction means positive. So, but positive negative, it becomes negative, and that is 40 because it has a speed of 40. So minus 40. So all you have to do, just 340. Okay, divided by 340 minus 40, the answer is going to be 1.13. So the frequency that is observed by the driver of the van is going to be 1.133 times the frequency of the source. Now, which frequency or which observed frequency is higher? It is clearly this one here. So that is using some numbers just to determine that. Now we can see that clearly that the driver of the van will hear a frequency that is higher than the frequency of the driver of the car that is moving away from the fire engine. All right, so remember this. That would be the end of our session, but I would like to give you a summary or a recap of what we've learned before we end this session. Inshallah, next time we're going to start from question number 11. Yalla Baba, going back to this or from this, we've learned about the speed of sound in different mediums. Gutman, sound can travel through solid, liquid, and gas. It is the fastest in solid and it is the slowest in gases. The reason why it is the fastest in solid because the particles are closest. It is the slowest in gas because the particles are the furthest, you can say, away from one another. And then, of course, we also learned about Doppler effect too. Before that, of course, you can say we've learned about wavefronts. Masha Gutman, sound propagates in 3 dimension. And then after that, we were talking about the breaking sound barrier. Gutman, if the speed of the plane is less than the speed of sound, there will be no sound barrier. There will be no shock wave, Basha. But if the speed is the speed of the plane is matching the speed of a sound, then there will be a sound barrier and there will also be a shock wave too. But if the speed of the plane it is faster than the speed of sound, then sound barrier will be broken. There will be shock waves and of course these, or you can say sonic booms too, Basha. So there will be breaking sound barriers and shocking waves too. And then after that, we've learned about Doppler effect. We said it is the shift. That is the change in the observed frequency because or due to relative motion. As long as there is a relative motion between the source and the observer, there is a change in the frequency that is here, which we call the pitch. And that phenomenon is called Doppler effect. And don't forget, Doppler effect that can happen in every kind of wave, not just in sound waves. And remember the equation. Inshallah, next time we're going to solve more questions. Till then, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.